Finally, the thing we are all here for is actually making the circuit board. Let's get to it. But first, what is a circuit board? A circuit board, in this case, is going to be made up of a top layer of copper, a central layer of like fiberglass or prepreg, and a bottom layer of copper. So 2 copper layers separated by a substrate. You can get more exotic multi-layer boards. We're not going to work with that here. You can set that up if you really want. It makes it more expensive, and it's just generally not necessary for pretty simple circuits. Now, it's always good to work off the constraints. Let's impose a constraint on the board outline and mounting hole dimensions. So we're going to use a board outline of 60 by 50 millimeters. Select that rectangle tool, and we'll set the grid size to 5 millimeters. This will make it really easy to lay out. The grid is how we position things and how they snap in place. The board outline goes on the edge cuts layer. So in the right-hand menu, make sure you select edge cuts. Click for the top left corner of the rectangle, 60 by 50. And because we have that 5 millimeter snapping, it's like an exact 60 by 50. Let's put down some mounting holes so we can actually place footprints. And these are footprints that are going to be unassociated to any schematic symbol. You can find mounting holes by typing mounting, and I want an M3. I've already placed one before, but you can see that under the mounting hole library, the M3 mounting hole, which has a diameter of 3.2 millimeters for some clearance. So double click to select that, and I'll come down 5 and in 5 and place that. Now, importantly, select the part, strike E to edit, and check not in schematic. This is really important for things like mounting holes because, as you can see, if I place another one, edit this part, and don't have that checked, when we update our circuit board, if we have this checkbox checked, which is delete footprints with no symbols, if we have that checked, I'll click update PCB, and that footprint is just gone. So there are 2 options. You can either have that checkbox checked, not in schematic, or in your schematic, you can actually place a mounting hole symbol. And you'll select a footprint for this. Whichever option you choose is up to you and purely a matter of philosophy. I used to put them in schematics, now I don't because KiCad has this not in schematic option. Whatever you like, it's up to you. Just stay consistent, I guess. But I'm going to copy that. I've made sure that it's not in schematic, and I'll place it 5 millimeters in from each corner. And so that means if we select our measure tool, Control-Shift-M, or you can find the measure tool in the side menu there, I can guarantee that I have a 60 by 50 rectangle, and I have a 50 by 40 mounting pattern. Finally, I'm going to round these corners. Oh, actually, let's just take a look. Alt-3 to go into the render, and there's our beautiful circuit board, and our parts are just floating off in space to the left. I'm going to round these corners though, so I'm going to select the arc tool and snap to the center of the mounting hole, and just click, and angle increases in the anti-clockwise direction. So I'll click in the center of the hole, click where I want to start the arc, and then move anti-clockwise to complete the arc. Do that for 4 corners. Now I can select the rectangle, delete the rectangle, and just join it with straight line segments. Alt-3 back to the viewer, and we can see those beautiful rounded corners. Now it's time to arrange the components onto the circuit board. And this is something that you don't want to rush. You don't want to just slap these down, because it can really change how easy your life is later when it comes to routing the circuit board. When it comes to placing components, it kind of makes sense to keep them in functional groups. Just like we had in the schematic, it makes sense to keep all the power and regulation side of things grouped together and our signal generator grouped together, because those are the connections that are closest together. Now these blue lines that you see connecting the pins, these are the rat's nest, and this is how KiCad is showing you what needs to connect to what. You can turn those on and off with this button, and I recommend putting on curved lines because it can be quite helpful to break up that angular visual pattern with some curved lines. It makes things a little clearer for me anyhow. I'm going to start from the power input side, so I'll start by placing the connectors physically where I want them to be, because you often have your circuit interfacing with the outside world, so it can help to place those connectors first as hard points, and then I'll build inwards. So I'll start with the V-in connector and the servo output connector. And I know that I want the user to interact with that potentiometer, so I'll place that first as well. Let's start on the left-hand side with V-in. So I can click that part and I can drag it by holding. I can also strike M to move, and you'll see that it's snapped to the nearest pin. I might change my grid to something a little more forgiving, like 1 millimeter. You can also change the grid by striking N for November. So you can strike N to go down the list and shift N to go up the list. And I'll just set that to 1 millimeter and make sure that I have my orientation correct. I want those screws facing out of the board. That looks pretty good. The servo connector I'll put on the other side of the board, and I'll center this with the screw holes. That feels like a natural thing to do. So all I did there was hover over the center, and because I'm on a 1 millimeter grid, which is like a factor of 5, it means that I can land directly in the center, and you can see that little circular ring forming, telling me that I have locked onto an anchor. If I wanted to go down, I could drag with the mouse, or I could just use the down arrow key, hold down Control to go in jumps of 10. And Shift will move the screen with the arrows. So you can use those in combination to get very exact movements. I think it makes sense to put my potentiometer for the user down here. So I'll do the same thing. I'll move that potentiometer to about the middle and just back it off so that it's within the bounds of the board. Looks good. I might keep this over to the side just so we can reference that as we go. I'm going to distribute this connector to guarantee that it's right in the middle of these mounting holes. So I'll select all 3, then right-click, align distribute, distribute vertically. Great, that's exactly centered. I know that next we are going to connect through the diode. So we go from the screw terminal into the diode and then into the regulator. Now I can see exactly what this connects to with that curve rat nest line, but I can also strike the caret key, which is to the left of the 1 key, and that shows me that the next thing that I want to connect to is this diode. So I can grab that diode, strike M to move, and I'll just place that right near my terminal. Maybe down the bottom there makes sense. Then we've got the voltage regulator. And this is pretty convenient because I can see that 12 volts will go in, ground will connect in, and 5 volts could be trapped here, but we also have the large tab for 5 volts as well. So this is making a pretty neat little circuit block over here. We've got our LEDs, of course. And I guess I'll put those, well, it makes sense to keep the 12 volt LED on the same side as the 12 volt supply. And the 5 volt LED, which is this through hole one, can go on the other side. Now where's the matching resistor for that? I can strike the caret key and grab that resistor. Now there is a link between the schematic and the PCB editor. So if you get lost, you can also go to the schematic editor, select that resistor, and when you go back to the board editor, it'll have selected it. So at the moment, I'm not paying too much attention about orientation. I'm more grabbing functional groups. This 22 mic capacitor as well, I know goes between 5 volts and ground. So that's pretty useful. I'll keep that around. Now things are starting to get a little bit overwhelming with all these layers, and we can change the layer visibility. So one thing that I don't really need at the moment are the fabrication layers. This is more like a metadata layer that's never really used during assembly, but it can help you determine where components go because it shows the name and the value separate to what's shown on the circuit board. But in any case, we can turn off FFab and B fab, and it just removes a lot of that visual noise. Oh, that's so much better. Now we can see more easily how things are connecting to each other. Let's see, we've got this diode, this resistor, and an LED. I know we want this to be near the regulator because it's how we're commissioning the regulator. So I'm probably going to keep things like that. There's a nice 5-volt path to the LED, then down to ground. Likewise, this capacitor can go away for a bit. Likewise, this resistor, or rather this LED, is being fed by 12 volts. And then we have the resistor to ground. So I could position them like this. So we'll have 12 volts coming in, and then rotate that with the R key. Then we'll go through the resistor and back to ground. This capacitor C3 is our output capacitor. And so I can put that just right next to the component in such a way that the 5 volts will loop into it, and then the ground connection is just there, like available right there. So the overall impression I'm trying to give here is that you should put a lot of attention into positioning these parts to make your life easier when it comes to editing the traces. By keeping the rat's nest crossings to a minimum, you'll make your life much, much easier later on. So really don't rush this process. You can see I've created these nice tight loops for the voltage regulator and the supporting components. And now I'm just going to zip through and do the same thing with the 555 timer. Just a note on alignment here, I'm putting this filter capacitor right next to my integrated circuit. And you can see that I'm struggling to find that grid alignment. There are a couple of things that you could do here. You could strike the S key and set the grid origin at one of those pins, which will give you that location. Or you can just drag the component by one of its pins and line it up over the top of the part in question. Then you can strike M and just arrow key to the left, and now you've got this perfect alignment, so these connections can just go straight across. So in that way you can work outside the snapping limitations of the grid in a case-by-case basis. So you saw me there just placing the rest of the components to lay them out nicely. And at a few points there, I was dragging these silk labels around just so that they're not being overlapped by any other parts. You can do that just by selecting the text itself and moving it around. And you can see there's a line that attaches it to the part that it belongs to. Now it's worth mentioning, yes, we have a 2-layer board, and that also means we have 2 sides to our board. So while I'm endeavoring to keep all the parts on one side of the board, and I encourage you to do the same, you can place parts on the reverse side of the board if you have to. To do that, select the part in question and press F to flip it. And now you'll see the colors have changed. So these red pads are showing parts on the top of the board, and the blue is for parts that are on the bottom of the board, parts and traces. Any copper that appears on the bottom of the board is blue. And so now you could have the situation where you can have parts sitting on top of each other like this, where you have on one side the regulator and on the other side there's a capacitor. They're occupying the same space, just on other sides of the board. This can get you out of trouble, but it can also get you in trouble with manufacturing later on. If you're going to be assembling this on a hot plate, I would very much recommend having all parts on a single side of the board. But it may be desirable for things like connectors to be on different sides of the board, etc. Just, be careful with that. And referring to my data sheet again, this is the full counterclockwise position, so I really ought to rotate my potentiometer to this orientation, RR, I really ought to orient it in this orientation if I want the arc of travel to be inside the circuit board. And that means I probably want to, oh no, that'll be fine. Make a line of components like this. That'll be really easy to assemble. I'll put that over here. Nice. And we are ready to begin routing. We've been very careful with the component layout, so now we can begin routing, and it should just route itself. In general, with routing, you want to route the most critical things first. And this is a small and pretty simple circuit board, and it's pretty low speed as well. This is only running at about 50 hertz on this signal generation. So it's going to be a very robust circuit anyway, but I'm going to apply best practices and route the most important signals first. And I think that we can separate that into two requirements. There's the signal generation side of things. We want to keep short, tight loops on the signal generator. And then for power, we want to deliver a fair bit of power to this servo. I think the servo can draw up to an amp. It's not going to because it's unloaded, but best practices, right? So I'm going to start with these components, and I'm going to hover over one of the pads and strike X. That's to begin laying a trace. You can see we have this red trace. That is on the top side of the circuit board. The default traces are going to be just fine for all the signals that we work with. For very high currents, we'll need to increase the trace width, and I'll show you how to do that later. But for now, I can just click that directly to where I want it to go. And you can see that when I start a trace, it highlights the entire net, which makes it really easy to see what other parts this trace needs to go to. I can click, and that's a whole net already done. I can connect the potentiometer to that resistor. And if I don't like the way that anything looks, I can drag it around with D. D will maintain the 45-degree angle snapping, which is kind of a convention for circuit design. 45 degrees, it's not necessary, but it looks very consistent. We have this case where we need to cross, so I could find a way to serpentine that trace around, but instead, I'm going to put this trace on the back side because it's going to be a pretty short trace. So I'm going to press, I can press V, and that will toggle between front and back copper. And then I'll start that trace. And now you can see this trace is in blue. So when we go to our 3D render here, we can see the traces that I've been putting down like this. And when I flip to the back side, we can see that trace that I've put on the back side as well. Let's proceed. I'll probably want a top trace join for all of these pads. And then here I could put this on the bottom trace again. So I'll strike V and jump that to the back. This is the great thing about through-hole parts is every pad is an opportunity to route on the top or the bottom layer. If we didn't have that, then we would be laying a trace and then pressing V to drop a via, which then we can bring to the other pad. And you can see now we have a trace that's both on the top layer and then it drills down and then onto the bottom layer. But in this case, I have through-hole parts, so I'll just put the whole trace on the back side. Very convenient. That's the signal generation side of things. We can put in our power supply decoupling cap, and I'll preference to put as many traces as I can on the top side to keep a nice clean back side. Now here we have a signal that we need to run around. We've kind of painted ourselves into a corner. This is not a very critical signal though, because it's a low frequency signal, so we could route it around, but what I will do instead is sneak it. What can I do? I can sneak this between these pins or out here and then drop a via. So I can drop a via and then run it over to signal. And this is fine that it comes this close, but I probably don't want the signal running through my my signal generating side of things. So maybe it would be better to run it this way. Now that I've completed that run where I've passed under the two top layer traces, I can put down that via and bring it over. I can press D on that via to drag it around. And that's probably going to be fine. You know, here it might have been better if I undo those and I actually take this whole block and rotate it. So I'll remove this line by striking U. U selects the whole trace and delete that. I could actually rotate this whole circuit block. And this is part of the, part of the circuit layout process, is maybe it's better for me to do this. Because now I have a clean run for the signal, and that can just be on the top, which is my preference. I'm going to leave the 5-volt and ground connections for now. I've got something in mind for those, but now we need to fix the potentiometer. So the potentiometer needs to connect to 5 volts. That's okay. We can pick up 5 volts from over here. So now I need to run this trace for this signal. And this is where you start running into like design constraints and design problems, because we've got this trace that's spanning practically the whole board. And again, it's going to be fine. It's a simple circuit. But when you do something like this, be aware that you're creating a constraint. You can no longer pass traces horizontally unless you're on another layer. As it turns out, we only need to get power and ground across these two parts of the circuit board, so this will be fine. All right, turning to our power supply side of things, I'll connect up this LED with its resistor, connect the power, 12-volt LED, connect that ground. And so this might be where we want to include some thicker traces, because now we're dealing with power. So I can go to track and edit the predefined sizes. And we can define a size here. And you can use the KiCad's built-in circuit board calculator to calculate a size. I'm just going to be quite conservative and make this 0.4 millimeters. Now I have a predefined track of 0.4 millimeters, and I can draw that in. And you can see that it's substantially thicker. I've got an option here, and I could go to the LED somewhere on this track, but I'm going to go directly to the pad because that is where the current needs to flow. Ground, I'll connect directly. And then 5 volts we need to get over our circuit board. And this might be an opportunity to just cop out and go underneath. And then place a wire near the power supply. So we have a pretty short and straight run here. If I bring this wire over, I'm using the D key to drag. Now I can go back to my normal trace size because we're not talking about bulk power anymore. And that's when we can connect. That's when we can connect this 5-volt line. There's still a ground connection to make. We'll get to that later. And this one too. Go back to our thick trace. So I've got this dedicated high current path for the servo, and I have this low current path to drive the circuit. It's probably prudent to keep them separate. And I'm even tempted to bring the current path through this capacitor instead. And that way we have a bit of a star topology for power distribution. Now, once you're comfortable routing, there's a very cool feature of KiCad 7, which I'll show you. I'm going to delete these traces with U, delete, U, delete, U, delete. That's probably enough. I'll go back to the bottom layer. We don't have to manually do everything. We can just start a trace and then press F. And F will try to automatically complete that trace. Let's see that again. I'll go to the top layer, X to start the trace, and F attempts to automatically complete the trace. And look at that, so good. X, F. And so F has taken this serpentine path to avoid using wires. I don't want that. I'm just going to go to the next layer down, the bottom layer, and do the same thing. And now we have a straight path for those 5-volt signals. But that is a very fast way to drop a lot of traces very quickly. Once you've done all the critical stuff, you can just XF, XF the rest out. Okay, it's time to take care of the ground plane. At the moment, our board is just bare with a few traces going around. We're going to drop a power plane on the back layer. So you can find this Add Filled Zone tool and click, and we're going to select the back layer, the bottom layer, and we're going to choose the ground net. So we're going to add a ground fill or ground pour. And now I'm drawing a polygon. So I'll keep that as best I can to the outline of my board. We're drawing this closed shape. It is best practice not to go too far outside the bounds of the board for manufacturing reasons that you might come up against later. So I like to keep mine within the stroke, if I can, of the edge cuts. A little bit outside is okay. And then you can close the shape with double click. And I'll just drag that node down and drag that node down. So now we've got a ground fill on the bottom layer. And if I strike the B key to execute the fill or to refresh the fill, you can see that that bottom layer is now completely dominated by this plane of copper. And that's why I wasn't really bothering with doing the ground pins before, because I knew I was going to work with a lot of through-hole parts and execute that fill. So now when we zoom in on a ground pin, we can see it has this breakout. And again, things are getting a little bit noisy, so we should enter high contrast mode with H. Now H filters out everything that I don't care about. It only shows me the active layer. So I can click F to go to the front layer, and it's muted the colors of the back layer. And that can be really helpful when routing as well, because things get pretty noisy. But striking the H key again will take me through the 3 levels of high contrast mode. There's no filtering, there's like semi-transparent, and then it just completely mutes all other layers. And that works for every layer, including the silk screen. So if you want to just focus on art, this can be very helpful. For instance, now I'll take the opportunity, I'll strike E, and I'll turn off these references, because the references for the component that's in a schematic, I don't need the mounting holes to be referenced by a designator. So I'll set those to invisible, and I'll clean up my silk a little bit. And it just removes a lot of the noise. I can see that I still have a 5-volt connection that KiCad would like me to put in. It's not strictly necessary because these are connected internally, so you could just ignore that violation if you wish. Now, there's no real reason not to. I could just put in a via and remove this trace. So I'm going to select the whole trace with U, delete it. I'm going to drag this trace out a little bit. And now I can drop a via. I can start a trace with X, drop a via with V, and put that into the ground plane. So I'll just hit escape. And now I have this ground connection going down into the ground plane. And that frees me up to make this connection here. Not strictly necessary, but it's a neat trick because you can use this for surface mount components where you have a ground plane. If the component is all by itself, but you have a ground plane, you can always just drop the via straight down into the ground plane. That's a very common routing practice, and it means that you have a very low impedance connection to ground, provided your ground plane is quite continuous. Here, there's only a few breaks in the plane, just these small breaks here, but then the rest of this plane has a very, very low impedance connection back to our ground terminal. So let's just press on. I'm going to run the design rule check now. We had the electrical rule test for the schematic. This is the design rule checker. This is going to check that you haven't violated any physical constraints, and we haven't. KiCad is set up with various rules on how close traces can get together, the minimum sizes of traces, the minimum distance between other features like copper and the edge of the board. In general, the defaults are pretty conservative, and most manufacturing services should be able to handle them. My board has passed DRC, which means that I've passed ERC, I've passed DRC, and I'm pretty sure this circuit is going to work. I'm actually ready to get this manufactured. Before I do, I'm going to zip through and add some nice pretty artwork to it, put my name on it because I'm proud of it, and then we'll be ready for manufacture. Great, I added those graphic elements like the title, the version number, and I just added a few helpful debugging and quality of life stuff like some indicators for the 5 volt and 12 volt power, and also the input polarity and voltage range of the input, and some pin labels for the servo connection. Join me in the next video where we'll export fabrication files and we'll upload them to a fabrication service.